everyone. I would have waited a bit more for others to join, but the presentation today is a bit lengthy, so I will just start off by the time others can join us. So today's presentation is going to be another continuation of introduction. Welcome to the NPTEL course of Geographic Information Systems. This is lecture 4. Today we will be talking about mainly data acquisition. So we are going to learn more in depth about data acquisition, its generation, attribute data, display and investigation. So before we start with that, let us see where we have reached. So we are here now. Now we will be talking about data acquisition in advanced models, and we will learn about more advanced systems of GIS. So by the time we start with the lecture 4, we will be taking a brush up of previous class. So this is a brief summary of the previous class. So we learned about the origins of GIS and its timeline, how it is evolving as a very strong tool. We learned about telescope, printer and scanner, and also a mapper, which is a part of GIS. We learned about 6 major capabilities of GIS, that is data input, data management, manipulation, data analysis, its modeling, and the display output that we get from GIS. And we also learned about the current state of art platforms for analyzing the data in GIS. So we will quickly take a look at assignment 3, and the first question was, which of the statement is true for discrete data? A. Clearly defined entities with clear boundaries. It can also be called as surface data, both A and B, none of the above. So the correct answer is A. Why A is correct answer? It is because continuous data can also be referred to as surface data or non-discrete data. So the statement which is true for discrete data is A. Second, which of the following is not correct about field-based ontology? A. Describe the world as a collection of spatial distributions of phenomena. B. Represents a continuous geographical variable over some region of the earth. C. A value can be determined for every point. And D. None of the above. So this was already explained in the lectures, and I think it was word to word present for Professor Eithel's presentation as well. Third, objects can be represented as continuous, discrete, raster, or database. So they can be represented as discrete data because objects are represented in the form of points, lines, polygons, which are discrete data, and they are also our vector form of data. Fourth, in a vector data model, vertex can be defined as edge, link, nodes, all of the above. So obviously a vertex will be your node, and this is definitely self-explanatory if you know a little bit of geometry as well. Fifth, advantages not associated with tropical data model are spatial analysis can be performed without accessing coordinates. B. Stores spatial relationships implicitly. C. Error detection is allowed, and D. None of the above. Uh, so the correct answer for these advantages not associated with tropical data model is B. That is, it stores spatial relationships implicitly, uh, whereas it actually stores it explicitly. 6. In case of spaghetti polygon model, coordinates for Q in the below mentioned figure can be written as. So the correct answer in this case is the last one, which is D, and this is how your spaghetti polygon model will be represented. So it identifies the features based on the x and y coordinate points. So that is one of the reasons why it is going to be written in that format. So this figure will actually help you relate to the answer. I'll just wait for 2 seconds in case you don't have the solution and you want to take a screenshot of this to understand it better and relate to your answer. Okay, moving on. So this is your 7th question. The disadvantage associated with quad-tree model is or are processing time, huge storage capacity, prolonged alteration. So actually all 3 of them are the disadvantages related to your pottery model. I'm sure you have seen this pottery model sample before also. So what happens is that in a pottery model, as represented in this figure, we see subdivisions in the map. So what happens that it has been subdivided into quarters to define the boundary of the area, whichever is your study area. It will be divided into recursively subdivisions. Now, because of that, what happens is that time taken to process each of the single grid or node is quite high, and it requires huge capacity as well. If you compare it with vector data models, which requires lesser storage space, in case of this, because it is going to actually go about all of the grids, the capacity required will also be high, and therefore the time taken will also be more, and there will be prolonged alterations because there are so many of grids. The eighth question is Dash describes the terrain surface including the above ground objects numerically in the form of XYZ coordinates. So A digital terrain model, B digital surface model, C digital elevation model, D all of the above. So your correct answer is digital surface model. So what happens, your digital terrain model is actually only the terrain. So if you look at this, which is the DTM, this is only the surface of the earth, that is the terrain. So if we see this color coding, so let's say this is one section of this particular diagram. So this bottom line is your terrain, which is represented by DTM. So the black line is black. So the blue line above the black one is your terrain, and above it, whatever object is there, for example houses, this has not been included, right? So it's just the surface. Now in a digit, this question is different again. Okay, so this list was given to me by sir. I really don't know how this coordination, this one. Okay, it was not there for you guys. So what question, this one? Okay, it will be great if you could just type it down for me in the comment section. Okay, it's a lengthy question, is it? Okay. Okay, so one is okay. I think that would be very simple, and you were able to figure it out, right? Okay, okay. Okay. Anyway, I'll just explain it to you because it's going to be helpful. So, in case of a digital elevation model, it's a generic term, so it represents the actual elevation, including whatever is on the ground surface. So, in case of the red line, it also includes the build-up which is there. So, the buildings inclusive is your digital surface model, or the model that includes your build-up, and the digital terrain model is only the terrain. Which of the following is correct? So I think you had this one. Uh, is this a question you had for 8? Okay, so we'll just continue. So your data structure should be raster is simple, vector is complex, data collection, raster slow, vector rapid, geometric. Yeah, so okay. Geometrical accuracy, raster is high, vector is low, data size, raster is compact, vector is large. So the first one, which is data structure, raster is pretty much simple because it's just composed of pixels. Vector is complex because it's more crisp, it's more precise, and it has more attribute values associated with it. The tenth one, an imaginary line on the ground joining the points having the same elevation at a specific interval is known as an isoline, triangulated irregular network, ridge line, valley line. So this is going to be an isoline obviously because isolines are imaginary. Alright, so for lecture 4, this is the uh, outline that we are going to cover. So we will start with your data acquisition. We will talk about data source while acquiring it, how you generate them, what are the different sources of collecting as well as generating this data, what else do you include in an GIS attribute data, and data display and investigation. So whenever we are talking about data acquisition, so first we need to understand what we are referring to as data, what is the basis of calling any piece of information as your data, how it's going to be helpful in the work that you're going to do. So you acquire data which is absolutely necessary, because many times what happens, the type of data that we require has some sort of legal points associated with it. It has some very sensitive information which is not accessible for everyone. So there are several government agencies involved. So although most of the data nowadays has been open to the public, but still there are some of the data which is not very easily accessible. So first of all, you need to sort what you're calling as data and why you require it. So some of these spatial data collection techniques includes acquisition from the ground up. That means you go on the ground, you collect it. Then you can collect it through questionnaires, maps, and calculations. You do a sample analysis in the lab and collect your data. And you also do in situ sensors and other methods of measurements. So ultimately, you follow this particular process. So you have the real world and you have the remote sensing sensors. You have an imagery data that is being extracted from the sensor. You analyze that data and you generate a spatial database for yourself. And from this analysis, so what happens is that after doing this analysis, you also go back and cross check the real world whether it is in coherence with what you have on ground. So basically here you have done a process to acquire and also to generate a spatial database. So it can be through the field survey, it can be through a hired surveyor, it can be digital or manually on paper, it can be uh, done through, let's say, some sort of sensors that are available to you easily, for example, your mobile phones, or it can be done through imagery maps or cartographies as well. Or you can digitally analyze it in terms of vector or raster data. So there are other image-based acquisition tools as well. We have also learned about these two terms earlier. So first is sensors, where you include your aerial cameras and space-borne objects, and the second is scanners, where you have the radar or lidar. So this is just a graphical representation of how your different forms of scanner on a camera frame that is used for these kind of image-based acquisition look like. We will not get into the physics or the mechanism of it. So these are some worldwide used data sources, and they have data for almost different parts of the world. We will also see which data sources are useful for Indian context. So I'm sure some of you, if you have worked a little bit on GIS, you must be familiar with USGS. So this is the Earth Explorer, USGS look clearly. Then you have the Global Visualization Viewer, which is also a part of USGS. Then you have Landsat Look. This is also very helpful. Like I would personally recommend that you try to go to each of these links and take a look and explore any random, or if you have any set of site study area in your mind, just try to find it. If you have the coordinates, it's even better. But you can also go on the map and make the rectangle at a specific position, and you can also explore that particular grid. You also have the LPDAC reverb, which is from NASA, and this is quite interesting. Then there's NASA data pool. This is also very interesting. Then there's Hazard's data distribution system. So this is, I think, I'm not sure if this is having data, like if it's having a lot of updated data in terms of Indian context. But if you search for American cities, you will get a lot of updated data sets related to their hazards. So you can just maybe take a screenshot, or otherwise this will also be uploaded in the folder where I keep uploading weekly presentations. So you can take a look at all of these websites. For more depth of Indian context, you have Survey of India portal. So, if any of you are planners or architects, you must have visited Survey of India to get your topographic sheets. So, topography maps are another form of data source, which are in the category of cartographic data. So, they were done manually, and even now, if you go to Survey of India, they provide you with physical maps. So you can visit this website and explore different parts of India on a scale of 1 is to 50,000. You get other scale maps as well, but this scale is available for free. If you require other scales, you will have to go to Survey of India's office. Then this is another example. I did not have a very good quality, so like, this is just a sample of how the map looks. So you can download it from there, or you can get the physical copy as well. Then you have United States Geological Survey, Earth Explorer portal, which I have initially shown you. So they are present in resolution for up to 10 meters, and they have Landsat, Sentinel, IRS, LIS, and many other uh, satellite data. So you can just go up there and you can explore. So once you open the USGS website, so this is how the USGS website looks like, where you have this option of searching your data. So first you have to put a geocode address, so where you want to uh, you know find that particular metadata. So basically what this gives you is a metadata. So metadata is data of the data. So you find all the metadata here for a specific geographical location. So you just have to enter your place or make a polygon here, a rectangle, or any random shape. You have those options. So once you're done with that, you will get all these options. So if you know the exact coordinates, you can put the coordinates. If you want to locate it on the map, you have to click on the option use map, and then you have to locate it. Then you have to select the timeline from which to which months and year you want to get the data. So all the data sets that will be available in your specified timeline, it will come in the form of a list. And when you will select one of those options from the list, you will get this kind of attribute value associated with that specific data set that you have selected. So this is like the metadata of that data, and this is how it will be located. So it will be located like a, square grid on this map, and then you can download it, and when you will load it in GIS, you will actually get to see this grid at the exact geographic location on your GIS software. You can use ARC or QGIS, either of them for that. Another good source which we often use, it is quite updated, although I would personally not say that it's very accurate, but in Indian context, you can genuinely get a lot of data from Bhuvan. So if you have used Bhuvan before, you will know that it also has your urban growth map, then it has your metropolitan cities map, it has your forest location maps, it has your climate change map, it has disaster support services, it also has flood warning maps, it has deltec region maps, then it has vulnerability zone mapping. So it has a number of maps, and you get a lot of free vector and raster data. In fact, if you're working on ArcGIS, there's an option where you can link your given data in the form of WMS layer. So it will be a raster data. For example, I'll just move to the next slide. So this is a land use land cover map of not exactly, sorry, a land use land cover map. It is actually a urban growth map of Kolkata Metropolitan Development Authority. So if any of you are familiar with this region, so you will know. So all these orange ones are actually the 1990 settlements of Kolkata, and as you move away to so it kept expanding. So as you move to the blue ones, it's actually the later settlements which kept on adding. So what is happening here is basically, let us say I go to urban growth link of Google, and then I select Kolkata from the drop down list. It has a number of cities, so you will have the option of selecting the city of your choice. But please keep in mind, it does not have all the cities of India. For example, this is small city which is located here. So I think it's here. Yeah, it's called Bojboj, but for Bojboj, that transformation data is not available. So you get it for KMDA, but specifically for Kolkata metropolitan area, you get it. But KMDA is actually from here till here. Okay, so it's up till here somewhere, but you don't have to get the entire data. So you can get some amount of data here. So once you are on this particular link, you have selected your city, you will have an option on ArcGIS where you can link this map on the exact geographic location as a WMS layer. So you can search how to link WMS layer in ArcGIS, and I don't think you can do it on Q. So if you're working on R, you can search how to link WMS layer of one on your ArcGIS. So there'll be an option, and you can link it as a raster file exactly at the correct geolocation, and then you can perform different analysis, or you can make vector files from it. So this is quite helpful. This is another example. So this is also a Google map, but it mainly focuses on your road network. So this is like urban growth. This is like a road network emphasized mapping of Google. Then you have OpenStreetMaps. So OpenStreetMaps or OSM is another source of getting free vector data. So here you will get most of the built up areas. You will have the road networks. You will also get the points where trees are available in your urban area. You will also get data of open areas, then the green areas, the water bodies, the river networks. So all of these, so if you're looking at the water bodies, it's going to be something like a polygon, a blue polygon. And if you're looking at the river networks or the road networks, it's going to be lines. Okay, so there's a difference in the type of vector data you have, so it's pretty good. But again, we have this issue that for Indian context, you will not get updated file at the micro level. So even in Delhi, so Delhi is quite updated on OSM. So if you go to a small part of Delhi, let's say I zoom into Connaught Place and I want to check if all the buildings are there or not. So if any of the buildings are missing, I'll have to make my polygons and complete my file. But for Connaught Place, most of the buildings are there. In fact, the data is pretty good. So you can actually get ready-made vector data from OSM. So you will just have to, like, there's a download option. Like you will have this option of downloads and API, something like that. So under that, you'll have to go select Asia, then you'll have to go and select India. So now the new form of OSM data, India has been divided into different zones. So you get separate data for the eastern zone, you have separate data for the western zones, and all right. But if like earlier when we used to work, I think approximately 5 years back, the data was like for the entire country, you had a consolidated data. So once you download the data for India, you didn't have to download it zone wise, but you download the entire country's data. So this is how OSM website interface looks like. So this is what I was talking about. So this will give you the exact coordinates of the screen at which I'm looking at right now. So this is again, this is mainly the Kolkata Municipal Corporation. KMDA is incomplete, so KMDA is more on the north. So like KMDA will be more bigger in size. So this is KNC mostly. So if you come here, the GeoFabric downloads, this option will give you the polygons or the vector data that you need to download. If you come to Planet OSM, Here you can find a lot of updated things which may or may not be visible on this map. So you can try this as well. Other sources, I have not used it yet, but some of my friends who work on Python and associated with GIS, and some of them who work on GIS and AI, they actually use these other sources. So I'm not very familiar with this, but if you're using something advanced like them, you can definitely check this out as well. But for a regular usage, if you're using absolutely beginner stage GIS and normal GIS, GeoFabric downloads is your go-to place for data acquisition. Now, another source of your data acquisition is Google Earth. This is quite common. At the end, if we are left with a little bit of time, I can show you how I have placed my data, my vector data on Google Earth. So for now, we will just go with the slides. I can show you that in the end. So here, Google Earth will again give you free vector data. In fact, you can download Google Earth Pro and then you also get the option of creating new data sets, right? So you can not just get the data which is available, you also get to uh, create data in Google Earth Pro. So some of the people who are not very convenient with using ArcGIS or QGIS and they just want to work with vector data, this particular interface or this platform is pretty good. You can actually create a lot of vector data for your analysis. But yes, this does not provide you a very wide platform for doing analysis. For that, you will have to go to GIS again. So it not just have 2D data, it also has some 3D data, which I will also show you later. Next, you have Google Earth Engine. So Google Earth Engine is an advanced coding interface of collecting your geoinformatics data, and it's pretty cool actually. So what you need to do here, you need to input certain codes to perform certain analysis and also to extract certain data. And Google Earth Engine codes will be available to you on Google and on YouTube. So if you need to use Google Earth Engine for a specific task, you need to know exactly what you're using it for. For example, I want to ask Google that uh, uh, extract the code for Google Earth Engine to perform spatial analysis of land use land cover for XYZ. Okay, or let's say I said for Janpat Road in New Delhi. Okay, so it will give you a basic code that is required for you to put in Google Earth Engine. So this works quite good. I'm not very familiar with Google Earth Engine, but my colleagues use it and it gives really interesting results. In fact, if you're using OSM to download and link data to GIS, if you can get your hands on Google Earth Engine, it will give you a lot of data which is not available on OSM, but Google Earth Engine extracts it for you through coding, and you can download it later. You can get your results, you can link it back to GIS and do your work further. So it is used to detect changes, map trends, and quantify differences on the Earth's surface. So Google Earth Engine, why it's more useful and why it's good, because it gives you updated data. It extracts data for you from live satellite imagery. It combines multi-petabyte catalog for satellite imagery and geospatial datasets, and you can also have online satellite image analysis on this link. So earthengine.google.com, this is where you can actually visit and check out how the interface looks like. So initially it might be a bit confusing or it might be a little bit challenging, but once you can get your hands on, it's pretty good. So these are some of combination outputs from Google Earth Engine. It gives you really good outputs if you can work on this. So this is Google Earth Engine and its combination with AI. So this is a particular research work that has extracted the number of reviewed or published papers on a specific topic. So this is just showing a specific distribution of a set of papers. So it gives you not just the mapping, but it will also give you your descriptive statistical analysis of your data. Then this is another example. This is Google Earth Engine extracting the rainfall data for Indian subcontinent for you. So this also looks quite interesting. This is another example of Google Earth Engine. So this is Google Earth Engine and climate change disaster. So this is mainly your coastal vulnerability zone extraction. So what this tells you is which part of the coastal part of specific location in India is climatically vulnerable due to change in climate. Okay, because of global warming, this region is become uh, climatically vulnerable. Then this is another beautiful example of Google Earth Engine and climate change heat map. So yes, definitely India is getting affected at a very high rate. But if you look at other parts of colder countries, especially the European countries, you actually see they are getting heavily affected. And one of the reasons why is because uh, we have a very temperate kind of climate. We have been a little hot zone from the very beginning because of our location, but this was a colder region. So the rate of climate change heat absorption that is taking place in these countries are pretty high as compared to India. Okay, so I mean it's almost the same if you consider the amount of heat waves that they are facing right now is much more than India. So the impacts here are much higher, as you can see from the map. Now this is another example. So now we come out of that. Now we are talking about Google Earth and we are talking about QGIS. So this flowchart is actually giving you a rough example of how you can extract data and you can take it to your different analysis models. Now what we are doing here, we are collecting SRTM and Landsat 8 data. So Landsat 8 data is the data that is collected by Google Earth. So you have Google Maps in your mobile phones. It is collecting data from Landsat 8. Then you have this SRTM data. Your SRTM data is actually useful when you want to look at the digital elevation model or the digital spatial model. If you want to generate those kind of models, you need SRTM data. So basically you collect core spatial resolution data through these two formats. So you get it from Landsat 8 and SRTM, and then you also collect wildfire conditional factors. So this is an example where we are actually doing a hazard analysis. So which hazard are we looking at? We're looking at wildfires. So we take other factors. So this comes from our literature review or from other secondary sources of data. We have a medium spatial resolution data. So Sentinel-2, it gives you quite crisp data. So Landsat 8 data is actually a coarse data when you have 90 meters of resolution. But if you talk about Sentinel-2 or ALOS, I think it's something around 25 meters or so. I'm not 100% sure. Please Google it. I'm extremely sorry. But Sentinel-2 data is quite crisp as compared to Landsat 8. I think it's something around 25 meters. So you input all these data together and you do a collinearity analysis. Why you are performing a collinearity analysis here? Because multicollinearity, because you have multiple data sets. All right. So all of these data are not coming from your GIS databases. Okay, they're not coming. All of these data is not coming from remote sensing. Some of these data is coming from other or previous studies that has already been performed. So you are taking data from other papers. You are taking data from satellite imagery. You're taking data from remote sensing. So collectively, when you're getting all these data, you are actually feeding it into your so you see the blue markings. So these two analysis you're performing in Google Earth. So how you can mix and match your software. This is just an example and a process to show you that you don't have to do all these analysis. I'm just trying to show you an example of a specific situational analysis that could be combined with two of our commonly used open source platforms. QGIS is also open source and Google Earth Pro is also open source. So you perform these two analysis on your Google Earth Pro and then you do your DST mapping on QGIS. So you get your data sets, okay? You apply machine learning and then you export your data, or rather you can say you import your data into QGIS. You get your other fusion maps, so you get near-base maps, and then finally you can validate your outputs. Okay, so it's always better to know multiple platforms of your data analysis because it helps you get better, authentic, and validated results. Okay, this one, yes. Yeah. Okay. Okay, okay. So I will tell you, this is not about doing this analysis. Okay, these are advanced methods. All right. So I'm not trying to explain advanced methods here. I'm trying to tell you how combining or knowing two different open source softwares that help you in performing spatial analysis. In this particular example, because we are talking about Google Earth Pro and we are also talking about QGIS, so I took an example that concerns with remote sensing data and it does a wildfire inventory data set accumulation analysis to give you where wildfires are actually taking place more. Okay, so that's what the output will tell you for this case. So what they have done here, they have combined analysis from two different sources. They have not done all the analysis on, let's say, only QGIS. They have actually done half of their analysis on Google Earth Pro. Okay, they've used it to create some sort of spatial vector models. Okay, the SVMs, and then they have applied machine learning there, and they have transferred that data set after getting the outputs from here from Google Earth Pro. They have transferred that data set to QGIS to get their DST fusions. Now, these DST fusions is actually spatio-temporal analysis that is giving them timeline-wise. Let us say, for example, this they are seeing after a gap of, let's say, every 10 years. So maybe this is 1980, 1990, 2001, 2011. Okay, so just for the sake of example, so let's say they are getting different fusions for different year, and based on that they have acquired. Sorry, you need to be a little louder. Okay, so it depends. For example, I was looking at a spatiotemporal analysis for an area which is highly urbanized. Okay, and it has reached a saturation point. So what happened when I started analyzing that site from 2020? Uh, No, from 2001. Okay, so usually what we do here is we work according to the census data so that all the analysis are in parallel, right? The demographic, the spatial temporal, everything. So I was looking at the specific site and the data uh, change which was happening from 2001 to 2021. So we don't have a 2021 census data. So what we did was we projected that data. Now, when we did that analysis, we saw that there was, so we got, let's say, these fusion maps or these temporal maps. So what happened? They look pretty much similar. It was very difficult to, point out the differences, especially on a regional scale. For example, this is a regional scale. It's not, urban. It's not what to say. It's not an urban scale or a city level scale. So this is a macro scale data set. Okay, so when we are doing this thing on a macro scale data set, what happened? We could not see much of a difference, but we performed the same analysis on an area which was originally uh, rural sort of area, and now it has become a tier 2 city. So in 3 decades, the change which we saw at regional scale was pretty drastic. Okay, so why am I telling you this example? The kind of fusion you are trying to see, if your site is not susceptible to that kind of rate, you will not be able to see that change here. You will not be able to get your correct scale of mapping or graphs or statistical outputs. The reason being, if I wanted to see the same change in terms of water, let's say how uh, the 12 o'clock heat waves are affecting the change in water body. If I try to see that in terms of inland water bodies in Kerala, and if I try to see that in terms of water bodies in Bay of Bengal, the results are going to be very different. The results are going to be quite drastic in case of Bay of Bengal, but not in case of Kerala, because the type of soil and water typology that is present for both the coastal regions is pretty different. Okay, so if I try to keep a tab of this temporally throughout a day instead of keeping it throughout a few years, then I will not be able to get desirable results. I hope I was able to address you. Yeah. Okay. Yeah. Yes, it will not. Yeah. Yes. Yes, absolutely. Okay. So this is just a graphical representations of your data. Why data is very important. All the information about data is also very important. So we will be talking about metadata. Metadata is all the data about your data. So let us say this is my data, and my data is also including a lot of very small details which are concurrent and which are also inherent to my data. If I take away even one single element from here, it is going to disturb the data and the data will get corrupted. Okay, so what is happening, so this is just a schematic representation of how you are going to, understand a specific data model, or rather I should say how you're going to go about the entire process. So what is happening, you have a situation. Okay, so in that situation, you are given a specific purpose. You have a method which you're going to follow for acquiring your aim to do any kind of work. Okay, but that work is in your context. Let us say it is related to your geospatial analysis. Now, after you have your observations or your data based on your purpose and methods, you will create a conceptual model. Okay, this conceptual model will be based on the methods that you have applied. It will be based on the relationships that you get from your different analysis. It will answer your research questions. It will answer whatever was your initial hypothesis, whatever you were trying to find out. For example, if I am trying to find out what is the effect of heat, what is the effect of climate change on heat mapping in India. Let's say just in India, not throughout the world. So I have a purpose. Okay, I have been given a situation. Now, according to the literature review that I have, according to the data sets that's available to me, according to the site visits that I have done, according to my own observations, I'm going to create a conceptual model and my question will be answered. Now what happens? I go to the background. So I have to do a background study, right? How so you do a back study. So you have to study both ways. First you start here, you create a model, then you have to go and do a back study to validate your whatever you are doing. Correct? So you get your situation, you create your data model. It can be based on certain operations, it can be based on certain investigations, it will have geometry, it will have attributes, depends what kind of data and what kind of analysis you are doing. Then what you're going to do, you are going to check the fitness of your data, whether that amount or that quality of data is adequate for the purpose or not. So let us say I want to check what was the land use and cover change in Dwarka and Delhi. I'm sure all of you know that place. So if you want to check in Dwarka specifically, and let's say I took Landsat 8 data to do that. Now, if I'm going to take Landsat 8 data, it's a very, very coarse data. So, when you will zoom into only Dwarka throughout the Delhi, if you're going to zoom into only Dwarka on a data set which has a resolution of 90 meters, you will probably not have adequate fitness of that data and your purpose will not be fulfilled. So, what you will have to do, you will have to go further, get a more fine data, maybe Sentinel-2 or Sentinel-3 data is going to suffice your purpose, and then you will have to check your fitness of data again. So you will have to perform your analysis, get your data model, and check if now your data set represents your purpose correctly or not. Right. So what you do, if your data is found to be not fit or if it's not adequate for the purpose, you assess the error, you omit whatever is your error. So in our case, in the example what we did, we figured out, okay, Landsat 8 is the problem, the coarseness of the data is the problem. So we go for a finer data. We go back and we create another data model from another set of data, right? So this way you process this, then you get your precision. Okay, you need to then understand whether all the attribute data, all the precise information that is required for the final output or display data, whether it is available to you or not. Correct? So you will just cross check, you will understand, and you will assess on your own if all of that is fulfilled. And finally, when all of that is fulfilled, you will have a degree of confidence on your output model, your documentation will be completed, and you will be able to say that, okay, Sentinel 2 data is the perfect kind of data that I need to assess the spatial analysis of Dwarka, and this data set creates a specific data model, and the land use land cover change that I have acquired from this data is approximately 75% better and more correct as compared to the Landsat 8 data model which I had acquired earlier, and therefore my documentation is complete with the data that is adequate for this purpose. Correct? So I'm sure you've seen this slide earlier on Professor Aithel's PDFs or notes in his presentation, which is there. So this is just for you to understand what exactly is metadata. Personally, when I was learning about metadata, it took me quite a bit of time because I took time to process what exactly is metadata. It was very confusing. But data also has a data, right? So, what is metadata? So, who is a metadata? So, metadata is created the data. Okay, so your data is created by the metadata and it is managed by a specific authority. It doesn't have to be legal or illegal authority. Authority word here does not mean that it is some sort of government body. It means the person who is any person who is managing. So if I make a polygon, my polygon has a metadata. Okay, my polygon is a data. So let's say my polygon is a healthcare building. So that healthcare building is giving me area and perimeter of that specific building. So that is my data. But its coordinates and all other data which is present inbuilt to the geographic specific location specific to that specific polygon is my metadata, and I am managing it. So I have the authority. I have created that data. Correct? So where is this data? So this can be location specific or this could be source specific. Correct? So what is it? Is the data content? What was the source data used? So it also depends. Sometimes what happens, I need a data, okay, and I need to change or tweak that data according to my purpose. So what am I doing here? I'm actually not changing the data. My data remains the same. What I'm going to change is the metadata of that data so that I can make it suitable for my study or I can make it adequate for the purpose I want to fulfill. Right? How are you going to do it? You need to know the method by which that data was created. Only then it is possible for you to change the metadata and make it uh, suitable for your work if you have to change it, right? In most of the cases, we use the way it is because changing metadata is kind of, you really need to know everything. even if you make a mistake in one of the systems, then it's corrupted. Okay. And when should you do it? Well, there's no specific time when you should do it. But you must know, if let's say I made changes to a specific metadata and it has corrupted, how do I bring it back? I really need to know when it was created. I need to have the timestamp. So there's a recovery module of every metadata. If you are working in cohesion or on the same platform where it was created, so you will have a recovery module where you will get certain codes. So it is very technical and complicated, but I'll still tell you. So in that code or in that timestamp, you will know when. So you will know exactly at which timestamp your original data was your original metadata was contained in the attribute of the data. So you will have to go back to that and you will have to like reboot it in a way. Okay. So core components of metadata involves your record information of the metadata, the identification information, the constraints information, data quality information, maintenance information, the spatial and referencing system, content information, and symbology information. So these are the core nine components of metadata. You can have additional as well. Depends on the creator. Depends on what all I have assigned as a creator. But these are core. Okay, you need to have at least these. So record is mainly telling you the timestamp. The identification is going to tell you the let's say the coordinate systems. Okay, the constraints will tell you to what extent it can be uh, pulled or to what extent that data is present. So you can't go beyond that. You can come within it, but you can't go beyond that. So it's a constrained information. Then your data quality in terms of let's say resolution. Then you have maintenance information. So maintenance information is basically how you reboot it back to its original format if you make any changes. Then you have spatial information. So here you have the coordinates and here you have the coordinate system. So coordinate is where you're giving your lat long, but coordinate system is in what geographic coordination system that lat long is in. So you have several systems in GIS, you have WPS. Okay, so there are different coordinate systems. So this spatial information will have that system. Then you have the reference. So this reference is the point at which that particular metadata is point at which that metadata is stuck on your GIS timestamp, and the content information is going to have all the contents that is related to that metadata. So if I have a polygon, I may give the area also in the attribute content information. I may also provide the perimeter. I may also provide that okay, in this particular healthcare center there are 200 workers. I may also provide that okay, it is super specialty healthcare. So all these content information are stored here, and you have a symbology information. Now, symbology information can be of various types. First, if I just make a polygon that I say is a building, a healthcare center, that means its symbology is made by that particular shape of the polygon. The other symbology, so in this case, symbology will include the color of the polygon. In sometimes what happens is even on top of a building we put a small rectangle as a symbology and we say okay, this is healthcare. Rectangle is a healthcare, circle is an education institute. So that way symbology might change as well. So symbology is also user defined. It depends on the creator. Okay, I will just take a break of 5 minutes and I'll be right back. So we'll be back at 7. Okay, so let's continue. So this is another example. So metadata stores all the information about your layer, image, or data. So what is happening here? We are looking at your metadata as a in the description tab of your item. So if you select any item on your GIS software, you go to the description or you go to its properties, you will see the information stored in ArcGIS metadata format that appears under this particular heading, and the information stored in the FGDC metadata format and appears under this heading. So FGDC is nothing, it's just a type or formatting of a metadata. So this is another example. You can clearly see that you went to this particular website, Geographic Network Explorer. You clicked on a specific geolocation. So in this case, it's in United States, and when you clicked on a specific geolocation, you got all these information. So this is the metadata that is associated with that particular geographic point that you have selected. So it will give you all of these kind of data, that who was the publisher. So this is the content creator or the person who has the authority over that data. Then what is the title of that data, which area does it cover, what is the scale of that specific data, the service type. So it's an image service, and the latest status service running. So this means that they are continuously updating this particular metadata, right? This is again another example. So this is from your art catalog, which is in ArcGIS. So here, if you select any specific layer and you come to your description tab and you open your catalog options, you will be able to see your metadata and its formatting in the metadata section. So it will mainly give you that in which format or in which style you need your metadata. It could be different. You can also export your metadata. So many times when you are writing research papers or you are publishing books, the publishers will ask you to provide metadata of specific geoinformation system or geoinformation data which is present in your study or research. So you will have to get all these information, and you will, for every map that you've provided or for every table that you've extracted, you might have to provide them with the metadata so that they understand what is the source of your analysis, what is the source of the data that you are trying to show in your study, right? This is again another example. uh, this one I can show you live also because I've just taken it from my home. So this is how your data can be digitized from ortho photos as well. So here a 3D creation has been done from the satellite imagery, and this can also be converted into your GPS data, your survey data, or to a specific coordinate. So what they have done here is they have converted it into a specific coordinate system data, and they have actually created a 3D map. So this is Victoria Memorial in Kolkata. This is Birla Planetarium. These are other buildings that are present on the main road. So I just kept this in focus because I was assuming all of you might know this irrespective of which part of the country you are from. Then this is another example. This was from Google Earth Pro. This one is from Bhuvan. So in Bhuvan also you have this kind of facility. You can actually get your 3D view of built-up areas, but only those which are available there. So you will have to go and explore Bhuvan 3D, and you'll have to see, and you can also tick mark these options whether you want to see these boundaries or not. So it's completely up to you if you just want this 3D data. So once you get this data, if you extract the data, you will actually get the metadata that is associated with that data. That means the original creator, whatever data they have put there. So maybe they have also put the material information. So they have put the material information for every block. They have also put the area information. They have also put the height of the building, and maybe they have also put what are the different so what are the number of floors on every floor, what activities are going on. So it depends on the user. Maybe none of this information is there, but maybe this information is also there. What you could do alternatively is with you can tweak the metadata. So let's say I download this, and then I say that no, I want to keep all of this data in my database. So I have got the basic 3D map. Now I will go and add metadata to it. So I'm not changing the metadata, I'm actually updating the metadata which already existed. So I will do all the other calculations and everything and keep it updated. So your data acquisition in GIS refers to the process of collecting, obtaining, gathering geographical and spatial data from various sources to build and update GIS databases. So data collection or acquisition is actually one of the primary activities, very essential, because if you have the wrong data set, you cannot process the other activities, right? So it's very crucial. You have to be careful, you have to be attentive to what kind of data you require. So GIS system is a system that combines geographic data in the form of maps, satellite imagery, aerial photographs, and survey data with your attribute data. We have spoken quite a lot about attribute data in the previous class as well, and that includes your population, land use, infrastructure information that might be associated with your geographic data. And this particular attribute data enables you to perform the spatial analysis, visualization, and decision making with respect to your data available. Data acquisition is a crucial step in the GIS workflow, as the quality and accuracy of the data collected directly impact the effectiveness and reliability of the GIS output, which I have already mentioned to you. Now, there are several methods to collect your data. We will be discussing this. I'm sure this was not there in Professor Reithel's slides, but I've just added it to give you a little bit of extra information. So, out of the several methods, we will be discussing a few of them. One of the most commonly used is your primary data collection. This involves direct data collection from the field. So, it can be done through surveys, GPS, ground-based sensors, or any other format that you want. So primary data sources could be through experimentation, it could be through questionnaires, schedules, observations, interview based, it could be random, it could be stratified, or it could be categorical or planned. So you need to do a primary data collection for this methodology. Then you have no, it is not actually raster data. It could be your vector data as well. Yes, it is more of attribute related data, but it could also be a geographic data. For example, if let me take in okay, so if I take this map, so suppose I have to do survey of people who are traveling through this road, right? So when I am going to do a primary survey, I'll have, let's say, a questionnaire which I'm going to ask to the people. I will also have GPS services with me in my mobile phone. So at every point where I'm going to do a survey, let's say I find one person here, I find another person here, I find another person here. So this is not just an attribute data, it is also a geographic data. I'm going to pinpoint every location where I have surveyed my people throughout this road when I'm going to do the survey. So it's kind of both. Okay, it's not always attribute, right? So okay, then we have remote sensing. This is just a word cloud of data that you can get from remote sensing. So if you will just sit down, ponder upon one specific data that you get from remote sensing, you will actually find all of these words making sense, because it is not just an imagery data or in satellite imagery that you get. You actually get all of these information from just one image of remote sensing. So we have talked a lot about remote sensing. I'm not getting into too much definition about it. Then you have aerial photography. So aerial photography here captures the images of the Earth's surface from aircrafts. So this is also another form of data, and this is how it looks. Then you have satellite imagery. So this and this could be 2D or 3D. They are quite related, but they are not the same. Okay, this is from aircraft. This is from satellites. There's a difference. Okay. This could also be on different scales. So this is like more of a urban scale. This is more of a neighborhood scale. So it depends on what kind of analysis you're going to perform. Whether you need this scale of data. This is a specific resolution of data, and this, on the other hand, is more detailed. So if you need something like this, you'll have to go for a finer satellite imagery. This is more coarse as compared to this one. So, what we are actually trying to see here when we are talking about satellite image, we are talking about aerial photographs, we are talking about remote sensing. So, we are getting the natural and physical coverage information of the surface of the Earth, correct? Then we are also getting the social sensing big data. This is extracted from our mobile phones. This is extracted from the traffic information or traffic data that is available. If you're working on POD or if you're working on transportation planning, we will need the traffic data. Then there is data on social media. So basically, social sensing big data is data which everybody is sharing through some medium, knowingly or unknowingly, and that becomes a huge data set, and it's actually huge. Then you have other auxiliary data sets. So these depend on your secondary sources, like whatever surveys the municipalities are doing, whatever data is available from the ground survey. So the height of the terrain, the height of the building, all right. So all of that data is your other auxiliary data. So the Big data and auxiliary data sets give you the land use information about human activities and socioeconomic environment. So collectively, you can use this data to get a bigger picture of your land use and cover. So this is like a, yes. Why am I calling it what? No, this is your secondary data. Yes, this is your secondary data. Correct? Yeah. Yeah, social one could be secondary, could be primary. So it will become secondary if you're getting it from someone else. It will become primary if you go and collect it yourself. Correct? Yeah. Like if you collect it from your own mobile phones through your let's say networking, then it becomes your primary data sets, right? But if I go to the traffic management office and I ask them for the traffic trajectories, then it becomes a secondary data for me, but it was primary data set for them, right? Yes, 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 yes. As long as you are the first hand collector of those data, it becomes primary for you. Yeah. Then we have these LiDAR, which are light detection and ranging. So LiDAR is another very useful method of collecting data, but we as what to say, as students or as lower level which do not have administrative access, we generally don't get our hands on this one. But yes, this is again another method which is used for acquisition of data, and this gives you a really accurate elevation model and terrain characteristics. It is one of the most known accurate methods to get this kind of data. Then you purchase data. So there is data purchase. So you can have some commercial sources or government agencies that sell your data. For example, if I go to NatMo, I don't know if you're aware of NatMo or not. So NatMo is for mapping services. It provides you different types, different class, different purpose of maps. So you can Google NatMo, which is NATMO. So NatMo gives you maps and data in cartographic form. It is a little old school. It gives you really old sets of data. It also has new sets of data, of course. So that you can get at a specific cost. So they charge you. They sell that data. It's not given out for free. So you can purchase your data. And the last one is you can crowdsource your data. So with the rise of mobile technologies, users are contributing spatial data through crowdsourcing platforms such as OpenStreetMap, right? So I am a user. Let's say I update a certain information and then I put it on OpenStreet, right? Then there is Google Earth. Google Earth also has similar kind of platform where people are crowdsourcing. So to collectively create and update GIS data set, anyone can update it and they can put it there for others to use, which is really generous. Many people don't do it, but if you can actually share this entire web, follow a web code framework, you can uh, get the data, maybe update it, modify it, make it more advanced, and then you can go back to that model workflow and give it back to the same platform. You are contributing to that data through crowdsource. You are distributing that information through crowdsource data to other users. Right? So how is it working? So humans are having a certain set of information. Okay, so mainly it is an interaction medium. Crowdsourcing is a online web service interaction medium to between humans and the earth data that is available, right? So we have several human activities like we are having traffic congestion problems. We have huge volumes of vehicles moving around from point A to B every day. We have a social segregation assessment. We have a different type of land use in every place. So on the other hand, what we have is a biodiversity and a conservation system that we need to maintain. We have a change in the terrain and landscape. We have a climate science. So there's a quality we need to maintain, and there is a fixed law and rules of system that we need to follow to maintain whatever we have on Earth. So, as a form of interaction in the maintenance of these two things, in order to mitigate all the problems that is happening, we have awareness programs. How are we doing that? Only when we have this interaction, we are creating a crowdsourced geospatial data where we are uh, distributing situational awareness to people. We are also doing evacuation and rescue in terms of any disaster. We are, identifying the affected areas and doing a damage estimation, that what scale of damage has happened now, what scale of damage might happen in the future, and when it might happen. Maybe it's going to happen after another 10 days. So, that is possible only because we are able to crowdsource this geospatial data which we have, and we are also able to uh, provide a community recovery, especially after a disaster, or especially in a crisis situation, even during stages like a pandemic. We are able to provide a community recovery due to this crowdsourced geospatial data. Then we have publicly available data. So, a lot of data you don't have to buy them, they are available to you free of cost through online portals or through um, physical mediums, like you'll have to go and take them, but they are available to you for free. And you have some existing data sets. So what happens, that many organizations, let's say the irrigation department, okay, they will make reports, they will do surveys, they will have their own database. So you can go and ask them for that data. So data acquisition may involve both new and old data, which we have already understood and we have talked about. To use these both data together for any analysis, specifically for GIS or for any geolocation, we need to pinpoint that data, and it is necessary to match these pinpoint locations. So the actual and the virtual should be same. They cannot be a mismatch. Additionally, both existing uh, new and old spatial data must be edited if they contain digitizing or topological errors. Now, what are topological errors? Now, these are different types of topological errors. I'm sure you have seen them earlier. So, what happens is that these are two vector data sets. So let's say these are two lines. Okay, so this kind of data set where one is on top of the other is called a tangle. Where one is stretched over the other, it's a switchback. Where one is crisscrossing the other, it's a knot. Where one is actually creating, a loop, it's called a loop. So a loop is called a loop basically. Then you have overshoots where one is crossing over the other at some point of the end, and it forms an X, it's an overshoot. And if it does not meet the other, that means the crossing is not taking place at one end, but there's a gap, then it's an undershoot. These are silvers, so you can actually see a gap between these two polygons. So what is happening is that uh, they are connected at 2 points, but at one point they are not connected. So they are creating a void in between, right? So these are different types of, so you have different types of redundancies in the nodes. You will have pseudo nodes, you will have redundant nodes, you will have duplicate nodes. That means there's already one polygon going, and then I create another set of polygon over that. So it's like you're duplicating the nodes, right? So you're creating one over the other. So overshoots could also be present, but then once you fix it, this is how it will look like. So this is your tangle, but once I fix it, it becomes a perfect polygon, right? Same is with your overshoots and your undershoots. So similarly, so these are just some examples where we are showing before and after, how it looks after cleaning. So it's very important for you to understand that you can do it manually, or you can do it with the help of commands as well. Usually when the errors are very small, like say in this case, we can just do it manually. You can edit your vector data, and then you start editing. There's a start editing option, you will go there, then you will just double click on this, you will see there will be points of this sort. So the points will actually look like these squares. Okay, so you will see square points. Usually there are no circle points, so you'll see square points. So what you can do is, if you've used AutoCAD, the way you take one node and you switch it over the other. So similarly, you can just pick this up and put it over the other one, and then it will be sorted, right? So these are just a few errors which are unpleasing, and it creates huge amount of variation in your data set analysis. These are just a few definitive parts of uh, uh, a polygon or a representation of a data. So this is your node. These are your ticks. So when you will be in editing format, you can actually see all of these. Then you have a label point if you have labeled anything. These are your arcs, so these are your arc editing points. This specific region is your polygon. So all these annotations, you can see them in your editing format, not in the normal format. So attribute data in GIS, we have spoken enough. So let us know a little bit more about this attribute data. So GIS has a database management system called DBMS, which is used to handle the attribute data within your GIS. These data are stored in rational databases, which are in the form of tables. Now tables can be prepared, it can be maintained and edited separately, but they can also be linked to data search and retrieval. So these tables are actually very important. So you should continuously maintain these data sets in your tables, and you can also do a lot of statistical or mathematical calculations in your tables. You can apply formulas. So there's a hell lot of things that you can do here, and once you have your specific data set, you can explore within it. So there are codes, there are commands to do all of those things. So mathematical statistical database related operations can also be performed, which I have already mentioned. So this is one example. What is happening here is that if you just consider your object, so I hope you can see the sky blue line. Okay, so your sky blue line is the sky blue which is selected here. So once you select one vector data on your polygon or anything, even a line, so that line will be highlighted even in your attribute table. So you will be able to relate that, okay, when I select this polygon, this particular area on my map, it is represented by object ID 49 and this dirham, and this is all the other metadata that is associated with it. Okay, so these are some statistical calculations. So mainly I think this is like your population in square miles, this is your population in 2003, this is your population in 2000, this is the total area of that particular polygon, then the number of white people, black people, Americans, Asians. Okay, so it has all the data associated with this particular polygon that is required for this particular study. Right? Now we come to data display. What are we referring to when we are saying data display? So as a representative factor for all map making plots, we have a final interface to GIS. Now this data display is an integral part of GIS because symbol, size, color, shape, all of these matter, and the pattern affects the user's perception and maps overall meaning. So how you want to represent what your data looks like, it will depend highly on your data display, how you want to display your data. So this involves selecting the symbol to represent your features. It also involves symbolizing the layers based on your attribute values, and the classification methods to represent your numerical values. So there could be a map, let's say if I consider this map, so these are different, let's say, districts. Okay, so all these black lines are dividing the districts. So I must know, if I want to represent this district according to the population of 2000, what is the kind of symbology and classification and color coding and the size that I give to my uh, graphics, so that my data display looks precise and it is also clear to the person who is trying to read my map. Okay, it should not be confusing, it should not be cluttered, it should be self-readable. Okay, so maps have certain formal methods of representation. Uh, these would be dealt in the 7th, 8th week of the course, so we are not continuing it here in too much of details. This is just a representation of your user interface of ArcMap or ArcGIS. So this is how it looks. So here are your table of contents. Then you have all your layers here. You can actually move your layers as well. You have a list of the layers and their drawing order as well. So you can always change the drawing order. You can toggle between data view and layout view. So this data view and layout view is like the uh, map view and the paper view in AutoCAD. So that's how this thing works. Then you have a data frame. These are your different tools. Okay, so this is a toolbar. So you use this one to select the features. This is for panning. This is for zoom in, zoom out. So these are different toolkits that's available. Then you have a catalog window. So what is a catalog window? A catalog window, you have to connect your catalog window where you have all your data. For example, I have downloaded my data set from somewhere and I have saved it in a specific folder. I'm going to link that folder. That folder and the other subfolders in every data that I have related to GIS that I'm going to keep loading, that I'm going to put in my catalog panel. Okay, so it's already there, you just have to open it, or if it's not there, you come to the window and you just select the catalog and it will appear here. And once you have your folder in place, you can just, let's say this is my data, I just select it, drag and drop, and my layer will come here. Okay, so these are different representations of how data is displayed. So these are different outputs of data. So this is just showing geographic point of a riverbed. So this is representing a river and just the contour mapping around it. Okay, so it represents a few land covers and the contours, right, and the geographic features which are available. This again can be, maybe it is representing states in a particular country that is affected by, let's say, malaria. Okay, so all the red ones are affected by malaria and the blue ones are not. So this is another representation. This, on the other hand, maybe represents all the major cities within a specific country. So all the blue ones are the major countries, all the red ones are the towns, and all the yellow ones are the rural areas. And these lines, fine lines that you see, are probably the major road networks. Okay, this again, maybe it is representing the heat island effect that is taking place in a specific region. This, on the other hand, maybe it represents something else. It is representing probably the migration points, how people from different zones are migrating to one urban center, so and so. Like, I'm just giving you how you can represent different forms of data in different display formats or graphical representations, right? So we finally come to the summary of this class. So we have learned clearly about the data set and data acquisition. Here we are looking at ground-based and image-based techniques. Now data source and generation can be done through several sources, out of which we have focused on USGS Earth Explorer, Google, OSM, Google Earth and Google Earth Engine as well. But Google Earth Engine, not everyone is familiar or comfortable with it, but I would highly recommend you to learn it. We have metadata and its characteristics, which were quite interesting. I hope I was able to help you out a little bit to understand that. Then we learned more about attribute data and relational databases. And finally, we understood data display and mapping, how the output of our data is helpful, how it is going to be important, and how it is going to visually represent your data without much of a hassle. Okay, so as we come to the end of this presentation, I will just show you one very small thing. Okay, so I just show you the Google Earth. Okay, so okay, I hope my window is visible. So this is how this thing looks like here, and Okay, so this is the actual Google Earth map where I had taken a screenshot and shown you this Victoria Memorial and its surrounding areas and how this 3D is available. Okay, so this is your Hooghly River. This is your Vidyasagar Setu, the new bridge. This is your Howrah Bridge. Okay, so I was wanting to show you how I had made one of the vector data sets on Google Earth instead of making it on GIS. So this is Bajbaj municipality. It's a small municipality, okay, which is right on the fringe area of Kolkata Metropolitan Corporation, and yeah. So you can see all my polygons are here. So um, I think there's another one. Yeah. So this is how it looks like. So what I have done was I had worked on two different layers and created two different formats. One was just the line segments and the other one was filled polygons. You can do with one also, but I required that kind of data, so I did it. So basically I have created these data sets on Google Earth. So this is a vector data format and I can clearly come here and I can save this data as place. Okay, so once I save this data, I'm not sure if that's visible to you. Okay, I think once I click on file, it's not visible to you, right? Okay, never mind. If you will click on the file, you will actually see the save option, and when you will go and save place as, you will get an option to save it in KML format, and then you can load this KML format in your QGIS or ArcGIS, and you will be able to do your analysis, whatever you need to do. So, if you're having a hard time creating polygons in GIS, or if your system is too slow, you can actually try this alternate method to create your spatial data sets, and then you will have to export it and take it to GIS, do your analysis, and also you will have to update your attribute database there. So I think that's it for today's class. And if any of you have any questions, okay, I think that will be all for today. Thank you so much for your attention. I will see you in the next class next week.